Hello, I'm going to characterize two perspectives of fraction knowledge, discuss their origins and implications of these perspectives. Knowledge of fractions uniquely predicts understanding and performance in algebra and higher mathematics. Not only in New Jersey or in the United States, but in many countries, students experience difficulty comprehending and operating with fractions. Now, these difficulties that students have coexist with current curricular guides, with textbooks that we use, with popular manipulatives used in classrooms, as well as with reform pedagogical practices. But all of these are based on a particular ontological and epistemological perspective for teaching fractions. So we're going to look at two different models for representing fractions and discuss the cognitive and mathematical attributes of each model. Model one will notice that in figure A and B, we have single quantities. In model A, we have a region that's been subdivided into equal parts. A certain number of those parts are shaded. And the fraction represented here, we can say, is 2/7. Or we can also say that these other fractions are represented by figure A. In figure B, the green point, which exists halfway between the fourth and fifth tick marks on the line, represents the fraction 7/8. But also figure B can be used to represent any one of these other fractions, for example. In model two, we'll notice that we have two distinct quantities that we're comparing. In figure C, we have a blue and a purple quantity. In figure D, we have a length that's colored light green, colored dark green, the other is orange. And they represent these Cuisenaire rods. And the Cuisenaire rods, the smallest is a white rod, and each of the other rods is a certain multiple of the white rod. And so the blue rod being equivalent to 9 white rods and the purple rod measuring 4 white rods, we can say that figure C represents the fraction 9/4, or 2 1/4, 2 purple rods and 1/4 of a purple rod, or these other fractions can be seen as represented in figure C. Figure D, we can take the red rod as the unit of measure and see that the dark green rod is equivalent to 3 red rods and the orange rod equivalent to 5 red rods, so that the fraction represented is 3/5. Or we can use the white rod as the unit of measure and say that the fraction represented is 6/10. And we have these other fractions, which are also can be seen as represented in figure D. So what are the cognitive and mathematical attributes of each of these models? Model one, we see that we always have one equipartitioned or discretized quantity or whole, that the model invites counting, a certain number of parts that have been shaded or the number of tick marks. The whole is implicit, or as a teacher once told me, preordained. The unit fraction is also predetermined. And so in model one, a fraction denotes a count of discrete entities, the number of highlighted parts to the total number of parts. Model two, the attributes are different. We have two distinct continuous quantities shown in each of the figures, C and D. In order to determine what fraction is being represented, it necessitates either estimating or actually measuring. One quantity is the explicit unit. The unit fraction, therefore, has to be determined. And here in model two, a fraction expresses a multiplicative relation. One quantity is measured by another quantity of the same kind. So these two fraction models, we're going to say represent perspectives. Model one, the partitioning perspective. Model two, we can call it a measuring perspective. Comparing these perspectives, we see that in the measuring perspective, we always have two distinct quantities, and there are decisions that have to be made in terms of which of the two quantities is the unit of measure. Whereas in a partitioning perspective, the whole is given, and it's already subdivided so that the unit fraction is also determined. So the partitioning perspective, things are given. The measuring perspective, one has to make decisions. These have origins, these perspectives. One is historical, and the other is philosophical. The historical perspectives brings us back to ancient Egypt, where fractions, written versions of fractions were first invented. We know that Egypt has these three major periods. In the old period, there was already evidence of engineering and written writing in ancient Egypt, where numbers, fractions, and other ideas were represented in hieroglyphics. We have, from the new period of Egypt, evidence of the instruments that were used for measuring. Here we have a cubic or a knotted rope used for measuring distances. Surveyors, you would stretch knotted ropes to measure the dimensions of a property. The knots were arranged in a uniform intervals. These are units. And when measuring a terrain, it was not always the case that it measured an exact multiple of the unit of measure. So when the unit, or the length rather, was not an exact multiple of the unit, there was a need for fractional lengths. And we can notice that the fractional lengths are multiplicative comparisons between two quantities, the dimension of land and the unit of measure. Later, of course, Greeks will note that the quantities had to be commensurate, that is, they had to have a common unit. Otherwise, the multiplicative comparison would result in an irrational number. So the ancient Egyptians had two forms of writing fractions. One was for writing unit fractions, where they used their symbols for integers with an oval above it. So here we have 1/3. The oval is above the hieroglyphics for 3. And then there were special fractions who had their own hieroglyphic symbols, 1/2, 2/3, 3/4. So those were invented about 4 millennia ago. But it took mathematicians centuries in order to accept fractions as legitimate mathematical objects. Eventually, it was understood that fractions could allow equations of the form ax equals b to have solutions, where a is not equal to 0, and that this would provide meaning for the division of any two natural numbers, and that it resulted in this closed algebraic system called an algebraic field. Now, the other perspective of fractions, the partitioning perspective, it emerges from a philosophical position that David Hilbert, the geometer, had, which he called formalism. And formalism was the idea of taking a finite number of axioms to build all of mathematics. Hilbert, being a geometer, was very impressed with the way axioms in geometry allowed one to elaborate geometric theories. And for him, mathematics is a game played according to certain simple rules with meaningless marks on paper. So the formalists maintain that the objects of mathematical thinking are the mathematical symbols themselves and not any meaning attributed to them. This philosophical belief permeated mathematics education. And as a consequence, the formalist idea of what rational numbers are was defined in this rather formal way. Rational numbers, represented as common fractions, are bipartite symbols that express quotients or ratios of two whole numbers, a over b, such that a and b are whole numbers and b is different from 0. Of course, for the teaching of fractions in schools, this formalist definition of a fraction doesn't provide a visualization to students. And so a way of visualizing fractions was developed based on partitioning or dividing up area. And so we have these examples from textbooks in use currently where fractions are presented and defined using this area model and dividing up and partitioning area. This is the part-whole perspective of fractions. What are some implications of this perspective? One implication is that students oftentimes inappropriately apply their whole number knowledge to evaluate fractions, so that the fraction 1/4 is considered to be larger than 1/3 because 4 is larger than 3, or that fraction arithmetic behaves the way whole number arithmetic, so that adding 1/2 and 1/3, we just add across the bipartite symbols, and so 1/2 and 1/3 is equal to 2/5. Or that if we just partition a region, we can, and there are 3 parts, one part of it is considered to be 1/3. Also, the part-whole definition of a fraction, that is, by saying that a fraction is defined as parts of a whole, doesn't provide meaning for improper fractions. So that how does a fraction, an improper fraction, can be represented geometrically when the numerator says that there are more parts than there are in the whole. Well, we want to also look at implications of implementing a measuring perspective. We have a certain position on what we call fraction sense, where the idea of magnitude is at the center of what it means to have fraction sense. We move from non-symbolic to symbolic visualizations of fractions. Flexibility and reasonableness are 2 important concepts that one needs to have strong fraction sense. And those we can discuss in more detail at another moment. But what I want to point out is that there is an interesting connection between cognitive neuroscience and the measuring perspective, because there's a growing body of evidence that demonstrates that humans have a ratio processing system. That is, this neurocognitive architecture that supports comparing magnitudes of 2 non-symbolic ratios. And that there's an important link that can be made between the non-symbolic continuous models of ratios and fractions and the symbolic version of fractions. So our question in some research that we've engaged with is, how can we help students use their reasoning about non-symbolic continuous ratios to think about symbolic fractions? In order to implement this perspective, we engage students in manipulating physical objects, Cuisenaire rods. We engage them in identifying the unit of measure, comparing and operating with these magnitudes, and later translating their ideas of these non-symbolic fractions into symbolic fractions. And we transition from what we call fractions of quantity to fractions as number. Of course, the materials that we're using are Cuisenaire rods. And we start off by having students manipulate the rods, and then without the rods present, write down what they have noticed about them. In this case, using inequality signs to talk about the absolute magnitude of different rods. These second graders also construct multiplicative structures in order that they can perceive and talk about fractions. So they look at and measure a rod with another rod and talk about the fractional relationship between the 2 entities. Here in this picture, we see that the students are selecting units and measuring the length of the blue rod. And what do they find? That an exact multiple of the white rod can be used to measure the blue rod, but not the red rod. But that the red rod is, the length of the blue rod is equivalent to 4.5 red rods. So the multiplicative comparison between 2 quantities becomes their idea of fraction. And they begin to use language to talk about things. The length of the purple rod equals the length of 2 red rods. Or in a shorter form, the brown rod equals 2 purple rods. And in terms of fractions of quantity, the length of the purple rod equals 1/2 the length of the brown rod, or the length of the dark green rod equals 3/2 of the purple rod's length and 6/4 of the length of the purple rod. They write their fractions of quantity expressions without the rods present. So these are expressions that are on the basis of images that they evoke in their mind of the rod relationships that they've been exploring. And then ultimately, they compare symbolically the magnitudes of fractions of quantities, such as this student writing on the board that 3/4 of the purple rod is less than 5/7 of the ebony rod. And other students contribute their noticings from on the basis of images that they've evoked in their mind. And that's what I wanted to present to you this afternoon. Thank you for your attention.